Hello and welcome to another session in physics. In this session we'll be looking at the topic electrical energy and electrical power. But before that, let us review the previous lesson. Welcome back. But let's start with trying to look at what electrical energy is all about. Remember, in our previous lessons we've said that energy is the ability or the capacity to do work. Electrical energy is not an exception. It simply means the work done in transferring electrical energy from one point to another point. That is basically the process that leads to the generation, the transmission, the distribution, and the utilization of electrical energy. And that's basically how electric light gets to us. There are some calculations that are very important for us to get ourselves acquainted with before we can proceed with this lesson. Remember, already we've said that energy is the same thing as work, and that it is the capacity to do work, and that it is measured in joules. We've gotten that point established. So electrical energy, or in other words electrical work, is given by QV. Of course, we know that Q at this point means charge and V means voltage or potential difference. But we also want to remember that Q is equal to IT. In other words, electrical charge is given by the current times the time. So if we go back to our first equation, that W is equal to QV, we just have to replace IT with Q, since Q and IT mean the same thing. So we're just going to have VIT. So if you don't want to use work equal to charge times voltage, you can say electrical energy or electrical work equal to the voltage or the potential difference times the current times time. Now let's go a little bit back to Ohm's law. Ohm's law is very important in this regard. From Ohm's law, we want to remember that we said V is equal to IR. That is, voltage is equal to the current times the resistance. Then we can now have the license to say that the electrical work is equal to the square of the current times the resistance times the time. These are equations we've been forming, so let's call this equation 1, and then let's call this equation 2. Let's call this equation 2, and then let's call this equation 3. We also have the fourth equation. The fourth equation from Ohm's law as well. From Ohm's law, when we make I the subject of the equation, we're going to have I equal to V over R. If we apply that to this instance, it means that electrical energy or electrical work is going to become W equal to V squared T over R. This is our equation 4. And the fifth equation, not necessarily the fifth, but more like a summary of all the equations put together, which we can use to find electrical energy or electrical work. The first one is the energy is equal to QV. It is equal to VIT. It is equal to I squared RT, and it is equal to V squared T over R. So using any of these equations, you should be able to find the magnitude of electrical energy or electrical work at any point in time. Now let's talk about electrical power. Of course, we said that power is given by work done over the time taken to do that work, and of course its SI unit is watts. It is measured in watts. Now I'm going to call this equation 5 since we stopped at equation 4 right here. So work over time gives us power, which is measured in watts. There are a couple of other equations we can use to find power, such as QV over T, that is charge times voltage over time, and then we have IV, which means current times voltage will also give us electrical power. And then the square of the current multiplied by the resistance will also give us the electrical power. The square of the potential difference of voltage divided by the resistance will also give us the electrical power. So any of these three equations, 4 equations actually, can be used to find electrical power at any point in time. Now let's talk about the buying of electrical energy, and this has to do with how commercial power is consumed by households, offices, companies, and so on and so forth. I'd like to point out that commercial power is consumed in a unit called kilowatt hour. Kilowatt hour. The short form is kWh. Kilowatt hour. Now let's try to point out something that's really important. When we say 1 kilowatt hour, we are talking about 3.6 times 10 raised to the power 6 joules. In other words, this is 3.6 megajoules, because mega means million. Megajoules. And if we want to calculate the electrical cost of using electrical power, electrical cost, or the cost of using electrical power, it's going to become cost equal to PCT over 1000. When we talk about PCT over 1000, here P means the power, total power consumed, C means the cost of the power, and then T means the time. Sorry please, this is the formula for electrical energy. Yes, electrical energy consumed is equal to the power times the time times the cost of using up that power, dividing it by 1000. The reason why you're dividing by 1000 is because 1 kilowatt is equal to 1000 watts, because kilo means 1000. Now when we say C here, actually what we mean is the cost per kilowatt. We mean cost per kilowatt. Cost per kilowatt hour. That's what we mean. The cost per kilowatt hour. And then of course we know that our T is our time, and our time is measured in hours. Okay. Alright. So at this point, let's try to practicalize everything that we've been talking about. A landlord has 8 40-watt electric lighting bulb, 4 60-watt bulbs, and 200 watts bulb. Now, if this man has all the points on for 5 hours and the distribution company charges 5 kobo, in Nigerian currency 5 kobo per unit, and we're asked to calculate what the bill is for 30 days. So first of all, we have to find the total power. Let me make this a little bit clearer. This is electrical energy that has been consumed. So if you want to calculate total electrical energy consumed, the cost of the electrical energy consumed, this is how it's done. Alright, so the total power that has been used by this landlord, we're going to calculate everything he has used in his house. Remember, he has 8 40-watt bulbs. So we're going to calculate 8 times 40. 8 times 40 gives us 320 watts. 320 watts. That's 8 times 40. Also remember that this man has 4 60-watt bulbs. So 4 times 60. 4 times 60 is 240 watts. And then we have 2 times 100, because he has 200 watts bulbs. 2 times 100 is 200 watts. So the total power used up by this man in his house is the total power is going to become the sum of all these things that are here. So when you add 320 plus 240 plus 200, you're going to have the sum of 760 watts. Now the time that was spent in using up all this energy was 5 hours every day for 30 days. So 5 times 30 is going to give us a total of 150 hours for 1 month, 30 days. That was the time the man spent in using this up. So the total electrical energy that was consumed by this man, I'm going to use E to represent that, it's going to become 760 divided by 1000, which will give us the units per kilowatt hour, and then we'll multiply it by the total time that's demand spent in using up all these appliances, and we're going to have 114 kilowatt hour. This is the total energy E that was consumed by this man, total electrical energy that was consumed by this man. Now we're asked to calculate what the bill will be for 30 days. What this bill will be for 30 days, we have to remember that if 1 kilowatt hour costs 5 kobo, then 114 kilowatt hour is going to become 5 kobo times 114, and our answer will become in naira 5.70 naira. So actually it was 570, but we just have to convert it to naira by dividing it by 100, and then we're going to have 5.70 naira. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.